Hi, I'm John Paul Raj, and I'm on a mission to make the learning of math fun. So if you're new to this channel, please do consider subscribing. On this video, we're going to talk about the geometry behind completing the square. That word square is a geometry term, right? So there's got to be some kind of a geometry involved in the algebraic method that we follow to solve a quadratic equation by completing the square. Let's find out. When we see a simple problem like this, x squared equals 9, 9 is a perfect square, and the term on the left-hand side is x squared, nice and simple, we can just say x must be equal to plus or minus the square root of 9, and therefore x must be equal to plus or minus 3. Simple. In the same way, if you have a square number just like the previous one, we can say x squared equals 25 must give us x is equal to plus or minus the square root of 25, and therefore x must be equal to plus or minus 5. And even if you had a weird number like this, I mean, there's nothing weird about 32. It's just that it's not a perfectly square number, but the process, the algebraic process, as we did in the first two cases, should be the same. So you should be able to write x as plus or minus under root of 32. And you can write 32 as 16 times 2, and that would just be plus or minus 4 root 2. Clear? That's simple. Now, if we were to extend this idea to a different level, a level 2 kind of a question, where you just had, instead of x squared, you had something square. We don't know what that something is. Something square, which is x plus 1, something square is equal to 4. You can use the same idea, the algebraic principle, and say, well, that something, whatever that something was, x plus 1 should be equal to plus or minus square root of 4. Which means that is a square number, a simple number, a friendly number that should be equal to plus or minus 2, which means x plus 1, that's something that we had on the left-hand side, must be equal to plus or minus 2, giving us x must be equal to negative 1 plus 2, or x is equal to a negative 1 minus 2. Okay, that on further simplification will give us x is equal to a 1 or x is equal to a negative 3. So those are the values of x which will satisfy this condition that x plus 1 the whole square, as we call it, that something square is equal to 4. Let's take another example of this kind. So instead of x, you had y. Let's say that something square on the left-hand side is equal to 5. Same algebraic principle. Something square is equal to 5. We can write that something, which was y minus 3, is going to be equal to plus or minus under root of 5. Now, we can't simplify that further. No problem. Leave it like that, which means y can now be written as 3 plus or minus under root of 5. Those are the two values of y which will satisfy this condition that something square on the left hand side, y minus 3 the whole square, is equal to 5. Y is equal to 3 plus root 5 and y is equal to 3 minus root 5. Let's take one more example of this kind. Okay, so you have x plus 2 the whole square, something square on the left hand side is equal to 15. Same algebraic process would say that something on the left hand side is going to be equal to plus or minus under root of 15, correct? Which means that x would be equal to a negative 2 plus or minus under root of 15. So that's as simple as that. X is equal to negative 2 plus root 15, x equals negative 2 minus root 15. Those are the two values of x that will satisfy this equation. Something square, which was x plus 2 the whole square, is equal to 15. Now let's change it to some other level of question where you use something like this, x squared plus a 4x plus 4 on the left hand side. Suddenly you've got x squared, 4x, and some constant here, another constant here, and this question becomes a little scary. But if you pay attention to it, this question and this question are the same. These two questions are the same. You just have to recognize that this term on the left hand side, x squared plus 4x plus 4, is the same as x plus 2 the whole square. Recognizing it algebraically using that formula a plus b the whole square, which we've seen before, a plus b the whole square is equal to a square plus a 2ab plus a b square. Now, this is something that we need to remember. Many times in algebra, we have to remember a lot of formulas such as this. And maybe that is the reason sometimes we find these kind of questions, putting us off. Suddenly we see three terms and we don't know what to do. But as long as we're able to recognize that this is actually a square, that square being x plus 2 the whole square. Let's just illustrate it using an actual geometrical shape, that actual geometrical square whose side length is x plus 2. Okay, we call it x plus 2 the whole square. It actually means that there's a square whose side is x plus 2. So let me just split this thing up. Okay, so it's such that this is going to be x and this is going to be 2. This is x and this is 2. And we can see that the side of the square, this is a square, x plus 2. Now, if you recall from that earlier video where you taught about the grid method of multiplication, let's use that technique here. All right, so these are the sides and that was a rectangle. And remember, a square is also a rectangle. This is a square whose sides are x plus 2. All right, equal lengths on either side. That makes it a square, which means it's symmetric. Let's use that grid method of multiplication now. X times x, that's x squared. X times 2, that gives us 2x. 2 times x, that gives us 2x. And 2 times 2 is a 4. And this then becomes x squared, 2x and 2x giving us 4x, and that 4. And now you can see clearly, pictorially, using the geometric idea that this term out here is actually the square, the area of the square, and that is equal to 15. So this question x squared plus 4x plus 4 is actually asking us, can you identify the sides of the square? That will give us the area x squared plus 4x plus 4. And as we've seen it before, that this question actually boils down to x plus 2 the whole square is equal to 15, and therefore must have the same values of x as we did here. Okay, so those are the sides of the square, x plus 2, the sides of the square being x plus 2, and the area of the square is x plus 2 the whole square, which is actually expressed in this frightening form. It's literally frightening. So if we were to use this idea for a question that's given like this, okay, that's how it's given when we are asked to solve in class. Okay, so suppose you had x squared plus a 6x plus 9 is equal to, let's say, 16. All of a sudden, it's scary. But if you were to interpret this question as saying, identify the sides of the square whose area is going to be x squared plus 6x plus 9. Let's use that same grid method and draw a square. Remember, we are drawing a square, not a rectangle. Okay, so equal pieces. All right, so those are the pieces of the square. The first term is x squared. That means that this area out here must be x squared. All right, the second term is 6x. And the square being a symmetric rectangle tells us that the second term, 6x, should be this piece and this piece combined together. So this can be a 3x and this can be the 3x. 3x plus 3x will give us 6x. And that's why we want its symmetry. We've also seen in an earlier video that symmetry is our friend. And this really helps us separate or divide that 6x equally, symmetrically. And that's why in the algebraic method, we divide. You know, we are always told b by 2. You know that method? Go and see my video on completing the square, the algebraic method, where we say divide b by 2. And the reason is because a square is a symmetric shape, a symmetric geometric shape, okay, a symmetric rectangle. And therefore, we know that this piece and this piece can be divided equally, giving us that middle term 6x. And then we want the third piece, 9, to be out here. If this is x squared, this must be x and x, giving us x times x, x squared. All right. If this is 3x, something times x should be here. What should be multiplied by x to give us 3x? Well, that should be 3. This is 3x. Something times this x should give me a 3x. So that should be 3. And 3 times 3 gives us 9. That means that the length of the sides of the square is x plus 3. And that means that when you've identified this expression as the area of this square whose sides are x plus 3, you can write it as x plus 3 the whole square, because the area of a square is side square, right? So this expression is the same as x plus 3 the whole square. Our right hand side was 16. And then this reduces to level 2 question, right? Something square is equal to 16. You can write this as x plus 3 should be equal to a plus or minus under root of 16, which can be written as x plus 3 is equal to plus or minus 4, and then you can solve it for x is equal to a negative 3 plus or minus 4. That should be the answer. All that we've done is that we've identified x squared plus 6x plus 9 as the area of a square whose side is x plus 3. Okay, let's take one more example. X squared minus a 4x plus a 3 equals 70. Okay, can you see this question? Now, because you have a negative sign, that might throw you off thinking about rectangles having negative signs. If you haven't seen my video on the grid method or the area model of multiplication, I'm going to link that playlist on quadratics. Please go ahead and take a look at it. It'll just give you a meaning to this grid method of multiplication, and it'll also give you a meaning to the geometry behind multiplication. Okay, but for now, this is going to be the area of a square. This expression, this quadratic expression on the left-hand side is going to be the area of the square. And we want to identify the sides of the square whose area is going to be given by this expression. Let's do it. Okay, so in the same way, let's draw a literal square, a geometric shape. And as we did before, let's split it up. Okay, and that's a square. All right, and what do we want? We want the pieces to be, this should be x square. We want something here and something here to add up to a -4. Right, so we can put a -2x here and a -2x here. So -2x and -2x will add up to a -4x. But the question is here. And that is the little picture of the square that we're trying to complete. That's why it's called completing the square. What should go here so that this is going to be a perfect square, an actual geometrical shape called a square? So let's work out the lengths of this thing, all right? So what should it be? If this is going to be x square, this side here should be x and that should be x. So x times x will give you x square. What should be the number here so that when multiplied by x will give you a -2x? Well, that should be a -2 because -2 times x will give you a -2x. What should be the number here which when multiplied by x will give you a -2x? Well, that should be a -2 again because that will then mean that the sides of the square obviously have to be equal, right? It's a square. X minus 2 on this side, x minus 2 on this side, which then means -2 times a -2, this number out here should be a +4, all right? But what do we have here? We have got a +3. And that is the question of completing the square. What should be the number here that will then give us a perfect square? We need 4, but the number in the question is a +3. Algebra says that there is a +3. We need a 4, so what do? Well, we have got a 3 here, so we can just add a 1 here. And if you add a 1 on one side, you got to add a 1 on the right-hand side. So which means our equation x squared minus a 4x plus a 3 equals a 70 can now be rewritten because of the square. Remember, this is the area of a square. We just said that this is the expression for the area of a square, right? And whose side lengths we've just identified as x minus 2, which means this is x minus 2 the whole square. If you've added a +1 here, you need to add a +1 there, and therefore this should be equal to a 71. Okay, now this becomes a level 2 question, and we know that something square is equal to 71 means that something which is x minus 2 should be equal to a plus or minus under root of 71. And then you can solve for x and say, okay, x must be equal to 2 plus or minus under root of 71. And those are the two values of x that will satisfy the given quadratic equation. There are a few things that I like about this method. Number one being that it gives me this conceptual idea of completing the square, a literal geometrical shape called square. What is that missing piece that I need to add that will make it a perfect square, the area of a perfect square? It gives me that idea that this is a square. It gives me a visual understanding. The second thing is that when we follow that algebraic process of completing the square where we have to divide that middle term by 2, we don't know why, we're just told, right? Divide that b by 2 and then you square it. Well, now you can see it when you are actually seeing a square as a symmetric shape, that this piece out here and this piece out here must be the same and they should add up to that middle piece, all right? So that will give us a clearer idea why we are doing those things rather than just being told procedurally divide b by 2. Okay, so I think conceptually it just gives us an idea and then we can work out what should be this piece and how we can adjust this. It was a 3 here. We can just add a 1 or whatever number you need to add. You make sure that you add on both sides and that completes the square. This method will not be required for any school exams, but this is only for those who want to understand the concept, the conceptual understanding of completing the square. Besides that, a square is a four-sided shape. It's a quadrilateral. This method, the completing the square method, is also called the Quadras Method, the method of completing a four-sided figure, a perfect symmetric four-sided figure, which is a square. And because of this method, the Quadras Method, that equation is called a quadratic equation. We asked this question in part 1 of quadratic equations. Why is a quadratic equation called a quadratic equation? I hope that this video has answered that question. I'm going to see you all in the next video.